So our next speaker is John Haymaker.
Great, thank you all for being here, and thanks to sponsors, organizers, and all of you for coming and listening. John, you couldn't have set up my talk any better about the need for conceptual design tools. I hope I can follow through. So the work I'm going to present here was work I did at Stanford. I recently left there and started a company. And like all professors, I'm really presenting the work of many people other than myself. I really tried to put together a multidisciplinary group of architects, engineers, structural mechanical, no electrical engineers, that would have been my next ad, as well as some mathematicians and decision analysis people. I called my talk Expanding Design Spaces kind of for two reasons. One is the design spaces we need to consider today are expanding greatly. 20 years ago when I was learning to be an architect, energy barely even entered the conversation. Material reuse was barely talked about. There were all these kind of weird guys down the hall in the architecture department who were kind of the environmental guys, and we sort of steered clear of them. We wanted to do the cool design. Now it's very much front and center. We need to consider environmental issues. We need to consider equity issues. We need to consider economic issues. So the things we need to consider are growing greatly. Also, all of the different options that we have to choose from. I learned yesterday that, wow, we have additive manufacturing now to consider in terms of the construction methods we're going to use, something I never even thought about 5 years ago. So all sorts of new technologies that we're dealing with, new ways to analyze all of these different spaces. So the potential space that we need to look through has grown tremendously, and we're starting to get tools that are going to help us search through that space more efficiently and effectively. So just generally get us on a baseline. How do good designs emerge today? Well, theory says we need to generate and communicate large design spaces. We can't rely on our precedent and say, hey, last time we built a building just like this, let's just do it again. We have to really step back, look at all the possibilities, search through them, understand trends, get to the best designs. So design space generally consists of 4 subspaces. The objective space, what are the things we're trying to achieve? In this case, we're talking about a high-rise in Switzerland, so we want the cost to be 150 million, about 150 rooms, an iconic building, view of the Alps, maybe some energy efficiency goals, maybe some other types of goals. And understanding which are most important. Is this really about energy efficiency? Is this about great rooms with great views? What are the trade-offs there? Next, we need to figure out what the alternative space is. We need to know kind of what the logical and geometric features are of this alternative space. We might be interested in this case, looking at a design that looks a bit like a ski pole, or perhaps one that looks a bit like a ski boot. We need to describe those things geometrically so we understand what the alternatives are. Next, we need to understand the impact space. Okay, how are these different alternatives going to perform in terms of all these different objectives we're concerned with and all these different issues? And then finally, we need to make some value assessments. We need to finally pick a design. Well, this one's better for energy, not so good for aesthetics. This other one's vice versa. Which one are we going to choose? Which one do we think is going to be most sustainable for us, our clients, users going forward? So good design decisions require efficient and effective processing of an amazing amount of information. And I tend to try to break it down into sort of 6 buckets, I guess. Who are the teams who are involved in this process? Who are our stakeholders? Who are designers? Who are decision makers? Who are the gatekeepers who can constrain this design space we're going to look at? Next, there are the objectives, the environmental, social, economic objectives that we're considering. We need to know about those weights, which are most important to who. How certain is all of this information? We need to understand our options. What are the alternatives? Who provides them? What information is available about each of these? We need to analyze all these options, again, for all these impacts. Finally, we need to pick out that design. It's really hard work, and designers today, out of necessity, take a lot of shortcuts, make some mistakes, and work inefficiently through this process. So let me just give you a couple examples. This is from just down the road at Stanford University on the Graduate School of Business. As we observe the process, this is something we would see fairly often, is inconsistency in the information. So if you look in one part of the file structure, you see that they made some decision matrix that said that for the HVAC options for one part of the building, looked like displacement ventilation was going to be a pretty bad idea. Go into the other part of the file structure and look at that. They got displacement ventilation all over this building. What happened? Maybe somebody made a mistake and missed it. Maybe there was some process that wasn't clear. But this information is very inconsistent. It can be very disconcerting for a large team who's trying to make sense of all the information and move forward. Why did they choose displacement ventilation? Another problem is we have difficulty sharing process information across projects. So in this case, the structural engineer on the project was asked to consider the life cycle environmental impacts of the material. Should we be building out of concrete or steel here? So we have this great Revit three-dimensional CAD, or we call it building information model now. And he went out and said, okay, I have this information, I have these quantities, how do I go about understanding what my environmental impacts are? He spent about 4 hours that he had in the design budget to work on it, couldn't find a process, gave up, never got the information to the owner, and they made a decision about structural materials without that kind of LCA information. Well, but as it turned out, this is a big multinational engineering firm. Over in Australia, they had a process already being developed and being used in some pilot projects, which could do exactly that. So the exact same organization couldn't communicate that there was a process to do what one engineer needed to do on one project. They already knew how to do it on another. Finally, firms tend to have a difficulty stepping back and saying, okay, on every project is unique. Let's step back and say, what are we doing over and over and over again? How can we start to find some efficiencies there? So here's an example where they have their architectural model. They have to go through a number of really what might be considered value-adding issues of generating that model, strategizing what they want to model, and interpreting the results of the daylight analysis. But then they spend about 12 hours doing what everyone considered non-value-added information, taking the architectural model, stripping it out, simplifying it, changing the geometry so it'll fit into the daylight analysis, running that daylight analysis. Okay, you do it once, that's 12 hours, but how many times do they do this on one project? How many times do they do it across many projects? The management had no clue. So just to sort of summarize the problem as I see it right now, we're doing very, very limited exploration of design spaces today in conceptual design when, as John pointed out, we can really make the big impacts. These are gross averages from a number of different observations we've done, but conceptual design can last in the range of about 5 weeks. Can be a team of about 1,800 architectural man-hours, very few mechanical and structural man-hours. We're really bringing those people, as John mentioned, after the fact to try to fix what we've done. Clarity requirements, really going in there and understanding, okay, what are the requirements? What are you guys trying to achieve? What are your energy goals? What are your space goals? What are your other goals? Very low, very hard to really figure out what those objectives are. They're in people's minds. They're in different Word documents, spread out, meeting minutes, and things like that. Not very good at collecting and communicating the objectives that everybody's trying to achieve. How many alternatives are we really able to model and analyze in a meaningful way to get good feedback from? We're doing, in the order of magnitude of 3 before we really fix on a design and try to fix that particular geometry. And the types of analyses we're doing really focused on architectural and first cost, not a lot of real energy and other issues. And we communicate our rationale as we go through these spaces very poorly as well. This diagram tries to say that we communicate the designers and the alternatives. Architects are great at getting up there and showing their pretty pictures and saying, John Haymaker and Associates on the side, isn't this a beautiful design? Let's build it. But all this other information, who are the managers and decision makers who are really involved in this? Who are the stakeholders we're trying to satisfy? What are their goals? Who are the gatekeepers? What are their constraints? What are all the analyses that led to our final decision of a design is not communicated well. So if you think about these kind of design spaces as consisting of objective space, alternative space, impact space, and value space, I'm arguing that generally the quality of these spaces and the clarity with which we communicate them is shockingly poor today. So how do we make decisions today? Well, we fall back on some maybe less effective methods, but ones that I run into a lot. We rely on precedent. We do what we've always done before. Rely on power. That guy on the thing slams his hand on the table and says, we're going to do it this way, let's move on. Persistence, the other person in the meeting says, no, I really want to do it this way, I really want to do it this way, and you finally just give in. Intuition, yeah, this feels about right. Approximation, well, might be this way, it might be that way, or we just try to simplify things and make decisions with less information. So generally, what are the research questions that I've been trying to attack with this team is how can projects teams generate and communicate better design processes, design spaces, and design decisions more effectively and efficiently. And it really has to do with being within the project on a project team and then these larger scales of across projects and across the whole organization. How can we start to manage these design spaces better? So I'm going to just very quickly give you snapshots of 5 tools that we've tried to build to expand some aspect of these design spaces or communicate them better. Talk about PIP, the process integration platform, MacDaddy, multi-attribute collective design assessment decision integration, design scenarios, requirements-driven parametric design spaces, PIDO, process integration design optimization, and finally DEAM, which is a design exploration assessment methodology. I'll explain each of those to you in a moment. So PIP, this is a collaborative tool. Basically, when we're collaborating on projects today, we're really looking at this, a file structure which breaks our information down into some kind of hierarchy. What's missing there is the process, all the dependencies between all of this information. So this tool does something fairly simple, just allows you to draw an arrow between files. So here we kind of have a high-level process where they're going through that teams and objectives and preferences and alternatives and impacts and value. And then each of these folders, for example, the alternatives breaks down into how do we actually define that alternative? Well, there was some preliminary information we went through. We built a couple of CAD models. Then how do we analyze those? Well, this is the analysis of the daylighting analysis, the energy analysis, life cycle analysis, et cetera. Break into the daylighting analysis. This is the process we went through for that daylighting analysis. So it's the opportunity for teams to get together and really map out the dependencies between their files, and we find that that's actually some pretty useful and interesting information. So it allows you to create and relate your information. Now, once you have these lines between them, you can start to search this information. You have more information to search, including the dependencies. You can say, hey, I'm looking for a process that starts with an architectural IFC model, a kind of standard data format that we have, and it has an output of LCA. Is there anywhere in this world of processes where somebody else has done this? So we can start to pull up processes in that way. And then finally, we start to develop some community and some metrics around these processes, people talking about how well they've performed, how often they've been run, and things like that. And through some initial tests of using these in classrooms and in some classroom design charrettes, we find that when people are dealing with their information in this way, there are more trend discussions. We start to see people talking about the trends of these spaces rather than just point designs. They tend to iterate through the processes a little bit more. They understand how their information relates to other information, and will therefore iterate through the process. Their information is more consistent, and the designers are less confused about what is really going on. Find improved sharing between projects as well, that there are less process mistakes, and people are able to take information from past projects and import it into their projects more successfully. And finally, this improved understanding across projects. And I'll just give you a couple examples of some views that we're able to create that I think are kind of interesting. So this is the class grades for a class project. Here are the different projects here and the different designers within each project. So basically what we can see here is designer 4 is sharing information with, no information with designer 1, but is sharing information with designer 3. So you can just see as a sort of generally rough view, we don't have any statistical significance on this, but it starts to show some correlation between how tightly people are integrating their information, how much they're connecting it, drawing these arrows, and the ultimate project grade. They're able to come up with better projects if they can work within this process view and understand how their information relates. And just another view, here we can start to look at specific tools and the information flow between those and start to understand that, wow, we're doing a lot of translation between AutoCAD and Revit. So let's go take a look at that across the firm and see what's going on. Maybe we should do some more automation there where we're helping the information through. Okay, so that's generally a process mapping and integration tool. This is MacDaddy. Again, a sort of 6-step process and tool that helps people formalize and communicate decisions. So this is the front page. You can see a series of decisions that we have there on the left. And I'm going to just quickly go through a high-speed rail decision here in Palo Alto. Decision here was whether we should tunnel the tracks through Palo Alto and build density up over the air rights to help pay for it, or if we should just build, as the current plan, an elevated track, which will go right down the current right-of-way of the Caltrain. So these are our 4 options, and this is a summary that says, according to this analysis, we should tunnel it and build mid-density around it. Okay, so how do we get to that? Well, the first step is to go in and model your teams. Who are your different stakeholders? In this case, we have people like Palo Alto government, people who work in Palo Alto but don't live there, et cetera. We can have different gatekeepers. These are building department people, perhaps Stanford University or other people who have the ability to really restrict some of the alternatives. We have the designers, and we have the decision makers. The next step is defining all the objectives, so getting them all on one page, trying to organize them and communicate them. And for each objective, for example, the ability to bike and walk, we start to try to describe what we mean by what would be a good solution for this. Say 8 miles of biking trails through Palo Alto. What would be a very bad solution? No miles of biking trails. So we can start to understand how we're going to measure each of these objectives. Now, there can be fairly qualitative, aesthetic, and other sorts of objectives. I feel it's important to get those in here as well. And if it's just we're going to ask the architect, that's a fine metric if we don't have anything else. We then send those objectives out to all the stakeholders, and they have the ability to weight them. Fairly simple process at this point of just trying to, you give them 100 points and let them lay their particular preferences over the different objectives. We can start to view that and understand, okay, well, what are the drivers on this project? Well, connectivity seems to be really a big driver on the project, and the ability to bike and walk to living and working environments seems to be very important to a lot of stakeholders, and we can start to drill in and understand who it's important to. Next, we want to just communicate what all the different alternatives are, give information about them. We want to go through a rigorous aspect of making sure we're analyzing all the alternatives for all the goals. Find we often miss, some of these analyses. We focus on perhaps just 1 or 2 of them, make decisions based on that. We then want to present something that we call value, which is essentially taking this idea of an impact of an alternative on a goal and multiplying it through that by the preference for that goal. So if you care a lot about something and it performs well, there's a lot of positive value. If you care a lot about something and it performs negatively, there's a lot of negative value. And we can drill into that information and really start to understand different stakeholders and what value they're getting from different alternatives. And start to drill down in that information. And for example, here see a comparison of increasing housing capacity versus ability to bike and walk, and see which alternatives are performing well in terms of just those 2 goals. Okay, so that's MacDaddy. The next tool is called Design Scenarios, which is really just talking about this process of, okay, we understand what our objectives are. How do we define an alternative space that's going to really well meet those? We could just sort of guess or have an informal process of getting from those down to the alternatives, or perhaps there's a more structured way to make sure we get a better alternative space that we can start to look at. So this is just a process of 4 models where we're going to first talk about some scenario logic. We're going to start with our goals, and this is what a real model will look like, and I'll just drill in just a moment. We'll go into that goal, and we'll start to break it down in terms of things like action items. How are we going to achieve that goal? Well, we want to maximize the unit exposure to water. We're going to control the unit orientation. We're going to calculate the percent of units facing water, and we're going to control the tower orientation. And then each of these break down in terms of some strategies and ultimately parameters, things that we can start to manipulate and wiggle around to try to optimize for that design. We then take those parameters, all right, and one thing that we get that's very interesting right there is we start to really already understand which ones of these decision goals are impacted by which ones of these parameters and things like that. So we can start to understand how our parameter is going to be impacting our objectives right there. And the next step is then to take those parameters and build a parametric model. So we'll take some of those parameters and group them into like perhaps the floor plate of the building, and then describe the geometry that will actually fit around those parameters and help us actually create geometry for it and constrain that geometry. And ultimately, so here's a model for a real project that we did with SOM, which shows we have the floor plate, which relates to the slabs and the unit walls, and the unit walls relate to the different glass walls in the south and the east and things like that. So we're starting to connect components of the building and describe them parametrically and start to generate these types of design spaces that are hopefully objective driven because we've connected them to the objectives. We analyze them, we bring them into a big spreadsheet where we put the different alternatives, the goals, we score them, and we understand how well they perform. Okay, so the next project is about going from alternatives to impacts and doing that more effectively and efficiently. So here we look to mechanical engineering, a technology called process integration, design optimization used in aerospace and automobiles. This is a platform made by Phoenix Integration. And we wrapped, you basically wrap commercial tools and then put them in this platform to orchestrate things like design space exploration and optimization. So we've wrapped Digital Project, which is an architectural flavor of CATIA, Energy Plus, which is the kind of leading energy modeler for us right now. GSA is a structural application made by Arup, and wrap it into a process flow like this. And we have an optimizer provided by Phoenix in this case. So our first attempt at this was to just do a very simple case, take a classroom building. You can see we're going to orient the orientation, the building length, the window-to-wall ratio, some parameters like that is what we're interested in looking through. And we're able to now start to get some really interesting performance trend feedback that just hasn't been available to designers until very recently. So this diagram is called a parallel coordinates plot. Basically, the blue lines are the best designs, the cheapest, and you can follow them through and understand that there are two building lengths, for example, that lead to the best structural, the cheapest structural solution. And here we're looking at trade-offs between structural cost and life cycle cost. So I'll just drill into a couple projects related to PIDO in a little more depth. So this is work by Ben Welly, and what he's trying to do here is to, John mentioned that Design Explorer is great for square buildings. We're trying to develop a more robust workflow which can work for more complicated buildings. So we're basically going to take the Digital Project CATIA model, put it through what's called an IFC translator, put the model into Energy Plus, put it into Radiance. You're going to take that daylighting information, plug that into the energy because you want to know how much daylight you need, so you know how much you need to turn on the lights, et cetera. And then we put it into this optimization flow. Give you a sense of some of the issues we have to deal with for this data flow. All sorts of things, like there are things called space boundaries, single level space boundaries, third level space boundaries. So you can see the difference here. It's just about how the thermal flow goes through the walls and things, that we need to set up that geometry differently for Energy Plus than the way it came out of the architectural model. We need to deal with the way we model things like columns and overhangs and fins, et cetera, differently. Energy Plus just expects different geometry than the architectural model. So we have a number of automated translations that work through that. And you can see the types of buildings that we're able to now push through this process and get accurate results. And now we're able to get this kind of information. We can understand that, hey, overhang depth on the west facade is the real driver. That's what's going to drive most of our energy performance. We can talk about these other things, but if we really want to focus on it, let's talk about overhang on the west. We can see some relationships between, for example, west overhang depth and south overhang depth and their trade-offs when you're considering annual energy costs. Second project is, this is structural. So this is a case where in a structural frame, you sometimes have continuous variables and you sometimes have discrete variables. In case of a structural frame, each of these members are going to be discrete. You have like a different size steel that you can put in there off the shelf. But the geometry itself is continuous, right? You can move it an inch up, or move this node back or forth or something. So in this case, we've developed a specialized optimizer which can do both the sizing with discrete as well as dealing with the shape optimizer issues. This is showing some moderate improvement over, let me just see here. Well, I'll just go to the next one. We were able to show moderate improvement over existing structural optimization algorithms. They've been around for a while, and so we can show for smaller problems some improvement. But the real issue is when you start to bring this into large projects with many, many members. So here's a steel stadium roof, and you can see that we're able to really reduce structural steel weight by a significant amount, 24% in this case. I show this example because I feel like there's incredible fat on our buildings. When people are using this technology in aerospace for airplane wings and stuff like that, they get super excited about like a 0.5% improvement. So there's real opportunity here. Just the last piece of work I want to talk about is, so as a designer, we come and we face different challenges. We might have fairly simple challenges of a relocatable classroom building in San Diego. We might have extremely complicated challenges of Google campus somewhere else. So we have a series of different challenges, and then we have a bunch of different strategies. We can just let the designer go and pick an alternative, and that'll be our strategy, or we can do some of these really advanced strategies that I've told you. And each of them afford a different type of exploration. So wouldn't it be great, as Hod mentioned before, to say, hey, I've got this problem. I want to pick this building design and plunk it in there. I think we need to take a step back from that and say, well, I have this problem. What's the right process for me to attack this problem? And so that's what this really work is trying to say, is can we measure challenges? Can we measure strategies? Can we measure the exploration? And we've just, I'll shoot through that, but we did a charrette test with allowing people to produce, given different challenges, apply different strategies, and we can measure their exploration and understand what strategies suit challenges the best. And just a couple of interesting things that emerged was that when we allow people to just get point data, so we say, give us a design, and we're going to give you the energy performance back. You'll look at that energy performance, you can give us another design, we'll give you the energy performance back. Amazingly, their exploration, their ability to achieve better designs was not much better than if we didn't give them any energy information at all. They just relied on their precedent. This is for professional designers, I should say. But when we start to give them trend data about looking through the whole space, give them the trends, then they're able to achieve much better designs much more quickly. So we've had some early efforts of really bringing these architects and engineers and stakeholders together. This is a charrette where I see a bunch of blonde heads there. We brought some researchers and professionals in from Finland. And in about an afternoon, we were able to go through this process with all these different tools and look through a fairly large space and get people to understand where the best designs might be for, in their case, a classroom building in Helsinki. So where are we now? I argue that we're getting a little bit better in terms of the quality and clarity of these spaces, but there's a lot of work to do. One thing I run into is building these models is a challenge, and people don't want to commit to really changing their process and doing something else, even if it will lead to better designs eventually. So there's this kind of ongoing research question about how much clarity and how much quality should this design space be for different challenges. So this is one tool that we built, which is just trying to show different options, the different stakeholders, and what the value is to each option. It's just one page. It allows these different stakeholders to go on and say, hey, I like this one because of this, I like this one because of that. And we can then compare and understand on just one page the design space without all that other detail. So just in summary, sustainable building design involves exploring and communicating design spaces. Project teams really struggle to do this efficiently and effectively today. We have tools emerging that do improve this exploration and communication, but there are great organizational, cultural, educational, and technical challenges remaining to apply this to practice. Thank you.
Hello, Douglas Eck from Google. I'm wondering if you could go back to one of the slides from PIP where you had all the big graph up. I'm going way back to the first third of your talk, I know.
Sorry about that.
That's okay.
Go ahead and start the question if you like, or I can.
So I'm coming at this from a software development view.
Yep.
And there are a number of graphical languages in software development that work for small problems.
Yep.
I can think of my area of music, and there are lots of great little software development platforms that let you pull together boxes and arrows and build cool things. And I would hold it to be almost a universal that these sorts of programming paradigms don't scale well. They don't scale well at all.
Yep.
And I'm wondering if you've had issues with, yeah, that's the one that scared me right there.
Yep.
That scared me. Oh no. Like underneath this or behind all this, have you thought about ways to take advantage of the paradigm of open source software development, which is really about building small reusable components of code and defining carefully ways for pieces of code to communicate with one another? Or is it that architects love this kind of stuff? I'm not saying it's bad, but honestly, for me as a software developer, I look at this and I think, I don't know how I'd ever spin up and be able to use something like that.
Sure, it's a great question. This is an exploration to see, how well can this scale to the architectural domain. Another challenge that we have is, in practice now, we have lots of people using lots of tools already. I mean, these are all commercial tools that we're wrapping in here, right? So I have done some previous projects where I went down to the very bottom and talked about the different components and how they should plug together and get the data to flow through automatically. I'd love some help from you guys to figure out how to do that better. This was really coming at it a little bit from the different side, which is, okay, we're starting here, right? We already have this folder hierarchy with everybody with all their information. And what we're missing, one thing we're missing is that, just knowing that something depends on something else, that gets completely lost. On a class project, working for 10 weeks on one design problem, this does actually scale pretty well, for the number of nodes and links and things like that. Some of the things that help are, we have a hierarchical organization as well as a graph organization. You can kind of work through either view when you want to, depending on what you need to do. So I found it did scale up to that level. I'm certainly interested in bringing that on to larger projects and seeing where it starts to break down and what the other issues are related to that. Okay.
Michelle Povinelli from University of Southern California. I think we've all had the experience where we've been in a building and you can see what the architects wanted to do, and you can also see which parts worked or didn't work. Maybe you see a collaboration space that was clearly meant as a collaboration space that no one ever uses, or chairs in the lobby that people don't sit in, etc. So I'm interested in how much data you have about which parts of buildings worked. There are a lot of buildings existing. There are a lot of buildings that have been built already. How can you get data about what worked and didn't work, and maybe use that to constrain the design process or guide architects?
Yep.
We saw the session this morning and yesterday was all about how if you have enough data, you can do feature extraction and start to guide designs. Do you have access to that kind of thing in this field, or what would it take technologically to start gathering the kind of data that could feed back to your models?
Great question. So we certainly have a process called post-occupancy evaluation, where we should go into buildings after the fact and understand how well they're working and record them based on the metrics that we used when we were designing. It's kind of a great idea in practice. Most projects kind of run out of money. It's usually in the construction budget, first of all, unfortunately, and then you run out of money and you end up cutting that out and don't do any post-occupancy evaluation. Another problem with post-occupancy evaluation, I think, is that the metrics you use to design the building get sort of lost. I mentioned that they're never communicated well. So then how do you go in after and say, well, is this performing based on designer intent or not? Because the designer intent is fairly diffuse and lost. So I guess I view the MacDaddy tool as, and I guess PIP as well, as the first step in that, which is in design, let's be more clear and structured about the way we're going to put this information together and present it. I haven't done any work in following this model through the construction and the operation phase, but I think it would be wonderful, I have these graphs of value. It would be wonderful if during construction people were, tracking all their decisions based on the value they're providing to the client, and as well in operation to return and say, are we really providing that value in the end building? Good question.
Roman Stalker, MIT. You mentioned that many of our buildings have too much fat right now. Yes. Given the uncertainty in sort of the design parameters and forcings and so on, how much of that fat is sort of needed in terms of extra safety, and how much can you really shave off?
It's a great question, and I'd love for some of my colleagues to jump in on that as well. But for example, structural engineering, I think what we saw there was there are already factors of safety put into these analysis packages, right? What is it, 1.4 and 1.7 for live and dead loads or something like that? So, there's already some factor of safety in there, and for that uncertainty, I guess. All of my work has assumed that the tools are good, and that there's certainly a lot of work to do to validate the energy analyses and the structural analyses to make sure that they are we don't have to add that extra factor of safety. But I think, you know, the work says we can include that factor of safety into the analysis tools if we want to, and then we should be able to optimize to that point and not add, you know, all these sort of softer factors of safety based on designers' intuition and things like that. Does that make sense?
Great. We have time for one more quick question.
Rahul Sarpeshkar, MIT. So this is a question for you and John, since there's no panel today. So trees have evolved over billions of years of evolution to stand tall and collect a lot of sunlight for their energy. And given that most of us are going to be living in cities in the future, which means we're going to have a lot of skyscrapers, do you think it's practical to build buildings like trees, where you actually have stuff that comes up and then branches out and then is covered with photovoltaics to have high roof area? Or do you think that would be extremely expensive and impractical to have all these branched structures coming off the building?
You know, certainly the discussion yesterday with the additive manufacturing, I have no precedent knowledge in what that stuff could cost, but that seems pretty promising that you would be able to you know, generate that kind of, I guess, complexity more easily and construct it more easily than you could today. I don't quite, you know what that looks like yet. But it seems like a big part of like building that thing would be the just cost of building such a structure and handling all those cantilevers and things like that. But with better structural analysis and better construction techniques, I believe we could build something like that and perhaps even do it in a financially feasible way. Really, I guess for me, the question would be, well, what are we going to put in that building? What does it need to do? You know, that says John showed that great thing about. Yeah.
And okay, maybe CEOs on the top. There's a lot of people on the top, but everyone's populating.
Can I just chime in real quick and say that branches sway a lot, and humans don't like that much acceleration normally, number one. Number two, there are setback laws because daylight is a natural resource, and if all the buildings create a canopy and the streets are dark, we're unhappy. So biology can do a lot for architecture in terms of inspiration, but we have to be careful just to copy directly and say, we've got it, buildings are going to be trees. But I agree that trees are an unbelievable work of technology that we're only beginning to understand. And if buildings could be more like trees and how they perform, absolutely. But we can't translate the metaphor directly.
Thank you, John.